Hello all, I welcome you all to the 24th lecture of this course E614. Previously we saw about metal oxide semiconductor interfaces and basic characteristics of MOSFET. We'll have a short recap right now before we go ahead and then see the final aspect of MOSFET that we will deal, that is the short channel effects. We will not go into a lot of detail in this because there is a special course dedicated to MOSFET um, device characteristics and such. So we will leave further details for that course, but we will just go into a very small discussion about what really happens and why there exists a short channel effect and such. Okay, so we will start with a very brief MOSFET recap because it will help us to drive home a few important points as well as to see why this short channel effects arise in the first place. The main architecture of MOSFET is that you have a gate which controls the electronic charge in the channel by electric field, right? So this is gate, this is source, this is drain, and you have a channel. And it is assumed in our previous discussions that it is the gate which determines the charge density in the channel to the most part, and there is only a very small perturbation from the drain side. So, and we calculated the charge along the channel. We took this direction to be x and the width direction to be y, right? The charge along x is a function of the gate potential subtracted by the flat band voltage and the threshold voltage, right? So this comes as a threshold minus del psi I of y. So this is the potential in the channel due to the drain bias not being equal to 0, multiplied by the oxide capacitance gives you the charge in the channel. And you also have additionally the depletion width in the substrate, which is written by 2 epsilon s QNA. This is again x, right? So so we have this expression for the total charge, and we know that the drain current is written by W by L integral 0 to L Qn of x V of x dx. So this is an approximation, right? So because first of all, okay, so let's see what this equation basically means. So what you do is you have a channel which behaves something like this. Instead of the channel being like this, you have a charge distribution like this, right? In the drain side it is smaller, and more the drain voltage is getting more and more pinched off, right? And the actual velocities of the electron goes like this. At the source it has 0 potential, and at the drain it has the maximum potential, right? So this is how the velocity gains as the electron moves from the source side to the drain side. So this being the velocity and this being the charge density, and the product of both of them gives you one constant current value across this junction. So basically this will be the total current, right? So this is what the integral basically tries to tell you, right? So you kind of take a mean of 1 by L. The 1 by L is the averaging out of all the, at each del x, the charge density multiplied by its velocity, right? So what basically happens is when the channel gets pinched off, right? So basically you have something like this. The carrier density drops to 0 at some point, right? So it means that if you really have to sustain a constant current across the channel, the electron here has to be accelerated to almost infinite values. So basically you have very high velocity in the region where the channel is actually pinched off to maintain a constant current, and it is this velocity which unphysical velocity that is assumed in the discussion that we currently had is the cause for most of the deviations from the theory that you find in the experiments. So let's go over one by one. Okay. So from this expression we actually calculated the total current, which turned out to be something like this. FB root 2 epsilon s q na by Cox this term contributes when you have potentials more than the saturation potential, causing you pinch off, right? So in the linear region it is this term which dominates, and in the intermediate region you have contributions from both. And as Vd increases further beyond Vd sat, this term starts to negate on the addition on the current that this term gives. So basically each of them balance out to give you a constant current in the region where the channel is completely pinched off, right? And we defined a region where if Vd is equal to Vg minus Vfb, that is the flat band voltage, minus 2 psi b, which is the charge required to, or the potential required to invert the channel, plus root of 2 epsilon s q na 2 psi b by Cox. So this is the potential which is dropped on the depletion width, and this is the potential which is required on the surface to invert the channel. And if this potential is available in the channel, you will have this depletion width, and hence you have a potential drop in the depletion width, right? So this is the explanation for why you have a condition like this, and this term is called as the threshold voltage, right? And if your Vd is equal to this Vg minus V threshold, we reach a condition where we have the saturation. And in the regions where the drain voltage is smaller than Vg minus Vth, we have Id expressed as W by L mu n Cox Vg minus Vt minus mVd by 2 into Vd. In the ideal case, m turns out to be 1, and m is basically 1 plus k by 2 psi b, and k is given by root epsilon s q na by Cox. You can see that this k is basically this term here, right? So if k by 2 psi b is just equal to 1 by root 2 psi b, right? And as long as psi b is a large enough value, m will be close to 1. So this is the explanation for these terms, right? And if Vd is greater than Vg minus Vt, where you reach saturation, we came up with an expression. Id will be written as mu n Cox W by 2L Vg minus Vth square. So either ways, in both in the linear and in the saturation region, we saw that the current is inversely proportional to the length, and hence it is the length which is typically used or scaled, is what we will see very soon, to increase the current. And why do you want to increase the current? As we saw in BJT and stuff, the cutoff voltage is inversely proportional to the is inversely proportional to the current. So higher the current, higher will be the cutoff voltage. So basically you can switch the transistor much faster if you have a larger current, right? So now let us proceed to the, now that we saw the reason for or now we saw that the expressions for the current, let's go and see what is called as MOSFET scaling, which has been carried out for some time now. So we have always been hungry for more and more transistors per unit area. So typically MOSFETs are scaled to increase packing density. If you have to do this, you reduce both the length and the width, so that you have more and more transistors per unit area. You pack more and more transistors per unit area. And why do you have an increased packing density? For increased functionality. You can do more operations for a particular area and such, and also for actually for mostly for cost, because the more transistors that you're able to pack on a single die, the more functionality that you can get, the more price that you can get. So basically you are more utilizing the raw material that you have actually put into. That is the primary reason when they started to pack things. But then the fact that you reduce the length, you have better electrical, you also have better electrical characteristics, in the sense that you have higher currents. If you have higher currents, you can switch faster, and hence your transistors start to operate at a much higher frequency, right? So all these reasons leads or causes an improved or all these conditions motivate you to reduce the length of the channel. But what happens if you reduce the channel length? There can be some consequences, right? So basically, does it adversely affect the transistor performance? The answer is yes. One such example of a trade-off is if the channel length L is reduced, this will lead to source drain depletion with coming too close, right? So basically you have a source and the drain, and you have some depletion width at the source, which is a forward bias junction, right? So you have a much smaller depletion width, and the drain depletion width is much larger, right? So this is drain, this is source, and if you start shrinking the channel length, there is a chance that source and drain starts to get closer. Now to avoid this, you tend to dope the substrate higher. When you dope the substrate higher, so basically the depletion width can now reduce, right? But then higher doping also increases threshold. Why? Because the depletion width is now much smaller. So basically most of your gate potential is screened, so to speak, by the depletion width. So you need to provide higher and higher potentials to actually invert the channel, right? Or you can also think it another way, that the intrinsic carrier density when higher substrate doping is actually much lower. So actually to invert it, you have to provide twice psi b, which is now higher, right? Because psi b is directly proportional to higher doping concentration. Now if you need higher gate potential, your oxide has to shrink, right? So basically if you have much smaller oxide, then you have a higher capacitance. Higher capacitance will give you a better, closer control of the gate onto the channel, right? So the oxide thickness has to shrink. But the problem lies here. You cannot reduce the thickness of oxide much further. We will see it soon enough, that if it goes below a particular thickness, then you start having tunneling between the channel and the gate and all sorts of funny business due to defects in the oxide and such. So now that we saw one particular example, the typical consequence of reduced channel length is given as short channel effects. And the first thing is VT reduction. Last time we saw that the VT actually raises. That's because you did something. You changed the substrate doping to account for source drain depletion with becoming too close. But we are just talking about if you don't change anything and just shrink the channel, what happens? You typically have VT reduction. This is caused by source drain charge sharing. We will see in detail what these things are. Second is what is called as drain induced barrier lowering. Third is subsurface punch through. All these things lead to VT reduction. The second aspect is ID does not saturate for VD greater than VD sat. So basically you do not have any saturation behavior. ID keeps on increasing. This is called as channel length modulation. We will see that also. The third aspect is ID is no longer proportional to 1 by L. So basically our previous equations do not hold. You do not have 1 by L relationship. So the smaller length that you have does not necessarily mean that you have higher currents. And the last effect of this is degraded performance with time. So you keep operating your device and after some time your device starts to operate badly, or it has some other effect because of some permanent changes in the device architecture that you have, right? So these are the common drawbacks of short channel or the scaling problems. So there are two different ways people typically scale. One is called as the constant field scaling and another one is called the constant potential scaling. But let us look at constant field scaling because that is something which is useful. People typically do what is called as constant field scaling so that the electric field in the channel remains the same. Why? Because they did not want to deal with velocity saturation effects. Doesn't kick in, right? So basically to avoid velocity saturation effects, you thought, achal, even if I shrink the channel length, I still will have the same field everywhere in the channel, so that I will have even if I have the current to be larger, I will have the same field so that I do not have velocity saturation effects. So in that case, what you do is, if length L is changed to L by kappa, the electric field is tried to remain the same. We don't change the electric field, remains E. Oxide thickness D is changed to D by kappa, right? To increase we will decide why. We will quickly come to see why it is 1 by k. The Vt is reduced 1 by k, 1 by kappa. Vd is reduced 1 by kappa. Vd is reduced 1 by kappa to have constant field E, right? Because if the length is reduced, you reduce the drain voltage to also 1 by k, so that the electric field is the drain to source voltage by the length of the channel, so that also remains the same. Right? Now, because the threshold is has to be reduced by 1 by kappa, or the length was reduced 1 by kappa, you change the doping concentration to kappa. So basically you increase the channel doping concentration. When you increase the channel doping concentration, the threshold actually increases, right? Now to do that, to accommodate for, but then if you want to keep the gate voltage the same, you have to reduce the capacitor thickness 1 by kappa, right? So basically, if you really have to go through all these scaling effects to such that you have a constant electric field, you have to reduce the thickness of the oxide by the scaling factor. You have to increase the doping concentration by the scaling factor, and you also have to reduce the drain potential by the scaling factor. Unfortunately, in the practical scenario, this never happens. Why? Because VD does not scale as well as needed. Why? This is just a technological issue. There is nothing fundamentally wrong about it, because VD is the voltage that is present from the outside. So most of the other systems do not scale as well as the MOSFET. So typically, or for some time, VD did not scale as well. But now if you see the actual technology nodes, VD has scaled much faster than what was anticipated. But this was an issue sometime before. One. Second, psi S and psi B are not strong functions of doping density Na, because if you will see that they are all bounded by the logarithmic relationship with the doping density, right, because of the Fermi relationship and such. So after some time, you cannot change psi S and psi B infinitely. We have seen this before. You can increase the doping density. That does not mean that you have increased the psi B. Psi B is the separation between the Fermi level and the intrinsic level, right? You remember, right? So this does not scale very well. And the third and the most important problem with this is the gate oxide reliability. Is not good below a few nanometers. Once the gate oxide is below a few nanometers, you started to have all sorts of issues with tunneling and all the defects and such. So these were the common issues which were faced when people were scaling. So now let us go and look at each of these problems in detail. In not too much in detail, because we will not go into numerics of this. I just avoided this intentionally because this is dealt somewhere else in detail. So let us look at, first is source drain charge sharing. So what happens when you shrink the channel? In the ideal case, you have an oxide, you have a gate, and most of the gate field, let's say that I apply positive potentials here. You deplete the channel first. This is the channel depletion width, right? And then you start getting the inversion layer. Now what happens is, you have the source and the drain also being the n++ regions, right? So what happens is, even you have additional positive charges here due to the depletion width, and there are certain so some of the channel gets, or the field lines from the source and drain, they stop at some of these channel lines, so that the gate actually controls a much smaller area than it controlled previously. If the gate length is very large, then these separations becomes negligible in comparison to the area under the gate. But then if the gate is shrunk such that the the channel depletion width under the influence of the source and drain diffusions becomes considerable. So you have lost these charges, and only this area is actually uh, under the field control of the gate, right? And hence the threshold voltage starts to reduce, because now more and more gate voltage is being used not to deplete the channel, but then to cause the inversion layer, right? The channel gets depleted by the support of the source and drain diffusion. So the gate is now useful only to, or a major portion of the gate potential is used to invert the channel. So basically this is called as the uh, source drain charge storage. It leads to reduced VT. And why reduced VT is a problem? You start having more and more leakage, right? So this is the first problem, which is called as source drain leakage. The second problem that we will see is called as drain induced barrier lowering. This is a much simpler feature. So we saw the band structure of the MOSFET before, and right now we are not going to do the 3D band structure, but just a normal one. Let us say that we will see this when the channel is not inverted. So you have a source, body, and the drain junction when VD equal to 0, right? So basically you have a N, P, N kind of a junction. Now if I apply an additional, if I apply VD not equal to 0, I will get something like this, right? VD not equal to 0 if the channel is long. But think about it when the channel is very short. So we will move this closer. So you will have something like this. Now any electron here, you can see that the barrier is significantly lowered, right? So basically if this width is much smaller, you have a punch through this, which is called as a tunneling conductance, as well as the fact that you have a much lowered barrier here. We saw this in several places. One is because of image force lowering and all such features, which causes the actual barrier height to lower in comparison to what it was before, right? I think you remember this feature in a metal semiconductor context and such, right? So this is called as drain induced barrier lowering, and this is seen both when you have an inversion as well as in subthreshold conduction. In both these things you have an increased conduction because of the fact that your the drain potential, higher drain potential, lowers the source body barrier. And it is usually measured by measuring the subthreshold current with the drain voltage dependence. Dibble typically measured by measuring subthreshold current with VD. So basically your subthreshold current increases as VD increases. That's because of the fact that you have more and more lowering if the potentials are higher, right? If you can remember, you can see that if VD is much higher value, you will have a much deeper lowering and much thinner barrier for the electrons to tunnel across. The third aspect that we will see is what is called a subsurface punch through. This is basically a consequence of our doping profile. So what we typically do in the body is doped in different profiles, in non-uniform profiles that we saw before. Is the most common doping profile is something like this. So this is in the y direction towards the body, and this is the surface, and let's say this is Na, right? So you have a lower doping density at the surface because you want higher mobility across the silicon dioxide interface, and you have an increased doping density just below the surface because you do not want drain to source sponge through, right? And you also have a reduced doping density below the body. Why? This is to reduce substrate bias effect, right? You remember, right? So if I increase, so if I have a higher doping density here, then I have a stronger capacitive coupling between the substrate bias and the channel, right? So basically I reduce this. But it also, what typically happens is this reduction in the substrate doping density below the surface will lead to what is called as the subsurface punch through, because the actual depletion width looks somewhat like this. This is gate, let's say this is source, and this is drain. The drain depletion width, the source depletion width is constant, but the drain depletion width, if as we saw, will have something of this shape, right? Because the doping density has increased below at certain y. So basically this is the y direction, right? So basically the doping depletion width increases below a particular thickness, and you can see that the actual thickness is much lower here, causing a punch through along this direction, which is subsurface. So this is called a subsurface punch through. This happens because of the non-uniform doping profile that you choose for optimized MOSFET operation. And the fourth aspect that we have to see is what is called as channel length modulation. It's pretty, I mean, the most simplest treatment is what we will see. So the ID at VD, SAT and higher is basically, sorry, mu n C ox W by 2L Vg minus Vt square. But however, one also has to remember that the length is now not L, because after it is saturated, L is changed to L dash, which is L minus del L, right? So under such situations, it is actually written as ID sat to L divided by L minus del L, which if del L is taken to be much smaller than L, can be written as ID sat plus ID sat into del L by L. So basically what happens is you have an increase in the saturation current as del L increases. So del L is the change in the length beyond the saturation point. So as long as del L is increased, you have an increase in the drain saturation current, which can be written as ID sat mu n C ox W by 2L Vg minus Vt square into 1 plus Vd by Va. This is in line with our BJT, where if you remember, even in the BJT we have something with a particular slope in the saturation region, right, which gives you a early voltage behavior and such. So you can write the same thing. And even for the MOSFET, you have a definition for what is called as the MOSFET early voltage. It is a measure of how much channel length modulation that you have in a device, right? So basically a small early voltage tells you that you have a very high channel length modulation effect. And last and finally, we will have what is called as a hot carrier effect. So in this, we once again go to the situation where you have the drain to be saturated. So you have gate, oxide, source, and drain, and the channel is pinched off, right? So what happens here, as we saw previously, the electrons are actually accelerated across the drain depletion width, right? And as the electrons are accelerated, we know that you can have what is called as impact ionization, right? So you have an electron hole creation. The electron is accelerated towards the drain, but the hole can now do various things, right? So the electron is accelerated towards the drain, causing you the drain current, but then the hole can be accelerated towards the source, right, because of the potential that you have applied, or it can be sunk to the body because both of them are at equipotential, and depending upon the body resistance here, the hole can be sunk down. In large MOSFETs where the length is much larger, you have a significant body current, or and in the case you have a very short channel MOSFET, you can see that the holes can be attracted by the source equally, right? So you have a major portion of current going to the source. And the third option that the hole has is to punch through the oxide and then form an oxide charge, right? So these are the three options that it has. And typically when Vg is almost equal to Vd, then you can see that you have a larger chance for the hole to actually be the hole and the electron, hole or electron, right? Hole or electron to be hole or the electron to inject into the oxide, forming oxide charges. And it is this which causes a degradation of the performance over time, because you can see that as time progresses, you can have more and more electron and hole being trapped hole and the electron being trapped in the oxide closer to the drain. So you have a time dependent degradation due to the hot carrier effect. There are some solutions which is used for reducing the effect of short channel. One is the non-uniform doping profile. So basically you have something like as we saw previously, from the surface you have something like this. You have a P minus, you have a P plus, and the P region. So you can play around with how closely this P or how small this substrate doping density is to avoid punch through and such, subsurface punch through and such. But this is a typical doping profile that is employed to avoid short channel effects where you have source drain charge sharing, right? To reduce the source drain charge sharing, you have increased the substrate doping profile, and that's what you do here. But if you do something like this, you have to reduce it here to avoid base effects, but then this will cause subsurface punch through, right? So basically you have to work around with this profile to give you the optimum solution. The second is you have gate stacks. So what people typically do is you have high K dielectrics which has a thickness much larger than silicon, but then the capacitance have an equivalent capacitance of much smaller silicon dioxide thickness, right? Silicon dioxide has an epsilon s of about 3.9, but you have a bunch of high K dielectrics like hafnia, aluminum and gadolinium and all those things, where you have much higher dielectric constants, something around 12, 15 oddish, right? You can have very high dielectric constants, so that the actual thickness is like 1/4 of so basically here if you see it's about twice, right? So basically it's about thrice. So the actual thickness can be 3 times the silicon dioxide thickness to have the effective capacitance in the same order of what you really want from silicon dioxide. The third solution typically that is used is what is called as a self aligned silicide process, or raised source drain, or recessed source drain. Here what happens is you have a gate oxide and the metal here, but then the source and the drain are raised. So you have a source, you have a drain contact, and the channel is along the surface here. So here you see that you have effectively avoided the source drain pinch off, source drain charge sharing, source drain punch through, right, and subsurface punch through, and all such effects. But then you have other issues with the gate field not being uniform across the channel, because the channel is now not a straight line but then has to go through all sorts of inhomogeneities that we have here, right? So this is called as a recessed source drain or raised source drain design. Another design is by SOI, which is called silicon non-insulator. The device structure looks something like this. So you have a thin silicon on top of an oxide. This is silicon, this is silicon dioxide, and then this is your substrate. The actual device is made on this silicon, which is called as a device layer. This is gate. You have an N plus source and drain, and you can see that now the body is significantly reduced, and you have only this much as the body, right? And now you have gate having much stronger control on the body, giving you the source and drain. You do not have a large region of the substrate contributing to the current, so you do not have punch through. Better subthreshold swing. Why? Because we saw the subthreshold swing is 1 plus CD by Cox, right? Now CD is much smaller, right? Why? CD is also small because the device layer actually is very mildly doped, because you do not need to heavily dope to have other sorts of issues with the source drain depletion touching and all those things, right? So the actual device layer silicon is very mildly doped, so the depletion capacitance is now much smaller, so you have a much stronger subthreshold swing. And the oxide layer, it is this oxide layer. Oxide layer also reduces capacitive coupling. With the body. But the downside of all these things is that it has a higher cost. The substrate itself has a higher cost, and because it's a very thin layer silicon, it has a poor material properties like mobility, and the oxide here also leads to very poor thermal conductivity of the device. So SOI thin film device is not great for power applications or high current applications, because the oxide below has very poor thermal conductivity. So with this treatment, we will stop here and then look at some look at some images of scaled silicon devices, particularly from TSMC and Intel, because it gives us a feel for uh, where the technology is right now. So this is a plot from TSMC, which shows that we were at about 3 micron in 89, right? And then we are at about 10 micron to 7 micron commercially in about 2019-20, right? And we started to come into 3D architectures somewhere lesser than 22 nanometers, where we started to have 3D FinFET and such. And before this, I think we stopped. We will go into details one by one. At some length scale, we switched from pure silicon to silicon germanium channels, and we started using high K dielectrics and such. By the way, the numbers here are called as technology nodes. They used to define as the smallest unit that you can define in a technology, but then the numbers stopped to make any sense after a certain point. Typically, it used to say how long your gate was, or it was about the gate was half the technology node, but then after some time the gate channel length did not scale as well as the technology node. So basically at 22 nanometers the gate was much larger than 22, right? So let's go here and look at 90 nanometer strain silicon. At 90 nanometers, if you see, the source and drain were actually made by silicon germanium. And what happens is when you actually cool down the device to the room temperature, the silicon and silicon germanium used to expand and then gives you a compressive stress on the channel, giving you better mobility, better hole mobility. So the PMOS had this kind of architecture, and for NMOS you had a film which was deposited on top of this device, and then when it's cooled down, it gave a tensile stress on the channel to give an NMOS better mobility. It is called as a uniaxially strained silicon. It was used in 90 nanometer silicon devices. In 65 nanometer and 45 nanometer devices, you can see that the silicon dioxide was replaced by high K dielectric, and the channels, you can see the source and drain were still silicon germanium to have strain in the channel. So you have a strained channel in addition to high K in about 65 and 45. And when you go to 32 and 22 nanometers, Intel actually went to this what is called as 3D architectures. So you have a silicon fin. So this is the fin basically, and you have gate all over it. So you have this. So this is a gate. So you have a gate which sits on top of the fin. So well, I don't know which one is the gate and which one is the source drain here, but it can be either, right? So basically you can have the channel here and these guys being the gate, or the other way around. But it is just to show that you have a 3D architecture, and then the gate now envelops the channel completely, so that the channel is now completely depleted even before you start. So basically your gate now has a better electrostatic control on the channel. And this is an image of the number of metal layers that a 10 nanometer transistor has. So basically this is a 10 nanometer device. I think it is Samsung, and you have the fins very clearly visible here. So I think this is the silicon fin, and you have an oxide and gate on top to define the channel characteristics. Right? So with this we will stop the discussion on MOSFET characteristics, and the next time we meet, let us talk about a small amount about heterojunctions, and then we will have a quick summary and conclusion. With that, I thank you for the attention. Bye bye.